test. Hey, what's up, crispy brownies? Are these chocolate brownies with chocolate chips and almonds? Chocolate is pretty good. Chocolate's amazing. For a dessert, if I'm given the choice between anything and chocolate, I'm gonna choose chocolate like 90% of the time. Even though there's some desserts that are growing on me, like a peach cobbler with lots and lots and lots of butter. Any dessert that has tons of butter. Ooh, Renee de Estes brownies. Yes, the brownies that mom makes are the best. If they have chocolate chips in there, that takes it right over the top. That texture, the extra chocolatiness, unbelievable. There's some dessert I had recently. I don't know what it's called. I mean, it has chocolate, but it also has, I don't know if it's tiramisu. I don't even know how to spell that. But it was something great. Now I'm hungry. I know. I'm sorry. I'm so sorry. To make you even more hungry, I had barbell wings last night. Have you guys had barbell wings? We have lots of wing options in Buffalo. I think, I would argue that barbell is the very best. This would be a very good discussion to have with people in Buffalo to see what you think the best wings are. But I had barbell yesterday. I think barbell's the best. Just their standard medium wing is out of this world. And the Cajun is probably my second favorite. They're all right, but I don't think they're great. Wait, Ranger, what's better than Barbell? Okay, you've only gone there once. There's now 2 locations. There's one in East Aurora, but there's one that's like on Main Street towards Clarence. TJ says Barbell is definitely top tier. I think Gabe's Gate is the best. I haven't been to Gabriel's Gate, but I have heard that those wings are fantastic. So I need to go there. I'm glad you reminded me of that, because you're not the first person to tell me that. What makes Gabriel's or Gabe's Gate wings the best? I mean, Duff's, no thanks. Anchor Bar, no thanks. They don't compete with Barbell, with Elmo's. Have you guys had Elmo's? I think Elmo's, those are Dr. Rehanian's favorite wings ever. Oh, right, tiramisu. I wanted to spell it like tiara. Yeah, I don't think it was just tiramisu, but I had something like this, and it had some like crunchiness and some more chocolate, and it was served in a cup. You eat it with a spoon. Okay, Gabe's Gate wings, they're a good size. The sauce is on point. To be honest, it's been a little while, but it left me with a great impression. Hey. You've convinced me. I want to check it out. Okay. Today, we're going to talk about some approximate models for lateral flight modes. I'm going to try to connect this to what we did last time as well. We talked about that the dynamics of an airplane, an aircraft. Oh wait, okay, question. Let me look at this question first. A question for the homework. How do we do we find X alpha in the same way as Z alpha and M alpha? Because X alpha expression isn't given. Let me pull this up really quick. Hold on, let me ban this. Good. Okay, so the question was, how do we find X alpha in the same way as Z alpha and M alpha? Because the X alpha expression isn't given. Hold on a second. What about X alpha right here? Did you see this? Do you mean the X alpha expression is given? Oh wait, I missed that part. Sorry. Okay, that's fine. That's fine. Wait, are you saying that X alpha isn't in the because up here I mention that expressions for these stability derivatives that you need, they can be found in table 4.2 in Nelson. So like, actually I have Nelson open. Oh, it's not in the textbook table. I see. Okay, I see what you're saying. So like X alpha, it's missing. So where the heck do I get it? Yeah. You just use this. Do you guys have other homework questions while we're on it? Yeah, this one's comparing the full longitudinal flight dynamics model to some approximate models. So today we're going to do approximate models for lateral flight dynamics. Okay. Yeah, but anyways, fundamentally, any aircraft motion, you could say that that motion is a superposition of its modes. Oh, another question. For question 2, is the aerodynamic moment delta M because it has a pitch perturbation, or is it all of them combined? Or are you talking about this? Sam Barry says, for question 2, is the aerodynamic moment delta M because it has a pitch perturbation? Yeah, what you should do here, like if you go to these equations here in the textbook 3.48 and 3.49, we have perturbations in aerodynamic forces and moments. So actually I have chapter 3. Where are these equations? Yeah, these guys. So these are the aerodynamic moments, L, M, N. What is this question asking? I think it just means solve for the whole vector. It says UB-MAE student. Right, I mean it's, if, like so delta Q, where am I going? That doesn't show up in delta L. It shows up in delta M, but it doesn't show up anywhere else, right? So the only aerodynamic moment affected by a pitch rate perturbation, that's what Q is. Only delta M is affected. So if more than one of these, if more than one moment or force happens to be affected, then include that as well. And UB-MAE student makes a good point. Like the most thorough answer is to provide the whole vector where some of the elements might be zero if that particular perturbation doesn't affect one or the other. Yeah. Drop my pen. You're welcome. You're very welcome. If you guys have any other questions, you can throw them in the chat, and I'll get back to them at the end of the lecture. Okay. So, whenever you're controlling a system, when you're controlling an aircraft, we're going to be getting into some controls in these last couple weeks. We're close to the end, everybody. We're a month away, because December 11th is the last day of class. So we just have a month left. But in emphasis on this last month, we're going to start looking at, okay, we've modeled aircraft. How do we start doing some control? Okay. Now, whenever you do control, it's desirable to have a low order model that you're controlling, like a second order, even a first order model. It makes the control system design easier. So when we're talking about longitudinal or lateral flight, we started with fourth order equations. For control purposes, we want to reduce these down. And so we're going to show some reductions for lateral flight modes today. And we're going to see how these approximations compare to the original fourth order model. Like, do they really capture the results? And actually, for most of these, I don't think the models are that great. I'm just going to level with you. They're not the best, and it might just be the particular aircraft I picked. So I picked a 747. We've been looking at that a lot, and these approximate models do not do the best. But I'll let you make your own judgment. We'll get into this. So there's going to be 3 approximate models we look at because there's 3 lateral flight modes. The first one that we're going to do is we're going to look at the Dutch roll. Now, this flight mode, if you were to look at it head on, an aircraft coming at you doing a Dutch roll, it kind of like, it's moving toward us, so it's getting a little bit bigger. But the aircraft kind of moves side to side to side, losing altitude, and it kind of rolls and yaws a little bit as it approaches us. So that's kind of what a Dutch roll looks like. Kind of this zigzagging motion, lazily falling like a leaf. So these approximate models that we're going to look at, they're from our textbook. So these aren't the only approximate models you can use. These ones are from Nelson. Oh, yeah, let me lower that music, Dilly. Yeah, let me know if it's distracting at all. Okay, you're very welcome. So this is how Nelson does this simplification. First, he's like, okay, I know that this rolls a little bit as it goes back and forth, but we're going to ignore the roll. So we're going to ignore delta P, which is like the angular velocity that pertains mostly to roll. And we're going to ignore changes in the bank angle itself. So we're only going to keep the lateral velocity and the yaw rate dynamics in our original model. So here's our original model. And we're going to employ this assumption right here. So we're going to throw out this roll rate equation. We're going to throw out this equation as well. Let's see. And because these second and fourth columns are going to be multiplying these variables In this case, we're actually going to eliminate these as well. So it only leaves these entries of our original model, okay? So we're ignoring the rolling dynamics. We're just keeping the lateral velocity and the yaw rate. Okay, so this is going to leave. Let's just take those 4 remaining elements and throw them in the second order. So we're going to have y sub v, y sub r minus u star, nv star plus ixz over izz, lv star. I'm running out of room here, but okay, nr star plus ixz over izz lr star. And if you're, I doubt any of you remember what these like star variables are, like these nv, nr. I don't remember myself. So I just wrote them down here, but basically, like this nv star, it's these inertia terms multiplying nv. And just to quickly remind you what each of these means, nv is the derivative of n with respect to the lateral velocity. So n is the yaw moment. So this is the derivative of the yaw moment with respect to lateral velocity. And I believe it's times 1 over the... Oh, shoot. I'm not going to remember which inertia term it is. I think it's like IYY maybe. Okay, but don't quote me on this one. It's like 1 over some inertia term times this partial derivative. Okay, so whenever you're looking at any of these stability derivatives, they have some either a mass or an inertia term. So I just wanted to remind you that those things are there. Okay, I'll put a question mark there. It's some inertia term. Okay, so we cut out 2 degrees of freedom, basically. We made this a second order model. Now, additionally, if we ignore this inertia term, it's going to simplify this a little bit more, because all of these star variables, they're pretty much associated with this IXZ term. So like, if I ignore IXZ and it goes to 0 in all of these, instead of having this NV star in my system, this is going to reduce to just having NV. Or whatever it is in either case. So let's make this assumption. And it's going to make our equation a little simpler yet again. And remember, each time you're cutting something out, you're losing some of the fidelity of your model. It's just a question of, does it still capture the basics of the real system? Let me pull up something really quick. So if we're talking about cutting out IZX, that inertia, let's zoom in here. You can see that this is minus 0.156 times 10 to the 7th slug times feet squared. So this is definitely, it's a huge number. It's not negligible. However, if you compare it to these other inertia terms like IYY, it's times 10 to the 8th. Same with IXX and IZZ. So it's an order of magnitude smaller. So that's why he's kind of like, can I ignore it? And that's what they do. Okay, so we've simplified this a little bit. Now, a popular choice, instead of writing this equation in terms of the lateral velocity, which is delta V, we can write this in terms of the side slip angle. So all of these variables are perturbation variables with the delta out in front, meaning they're small. So for small side slip and small lateral velocities, we have this relationship. So I could say delta V is just U star, which is my longitudinal speed, times a perturbation in my side slip angle. So if we take our first equation up here, this delta V equation, now I want to write it in terms of delta beta. So if you multiply out this first row, you're going to get delta V dot is YV times delta V, yada, yada, yada. You just multiply out that matrix. So if we take this and we use this beta assumption, this is going to become U star delta beta dot. So that's just the time derivative. Is going to be YV times U star delta beta. So I'm just substituting in this expression. Delta R. Now, what they also like to do is, now that we're writing things in terms of beta, this stability derivative YV, the derivative of the lateral force with respect to side velocity, we can write that in terms of beta as well. So like, this is the definition of that stability derivative, 1 over m times this partial. But if we write V in terms of side slip, assuming they're small, then we can do this. So I have 1 over U star times 1 over m dy d beta. And this is y beta. So I could say YV, that stability derivative, is the same as 1 over U star times Y beta. And we're going to make this substitution in for YV right there. Okay. So let's take this delta beta equation. We'll divide both sides by U star. I'm going to have 1 over U star times YV, which is 1 over U star Y beta times U star delta beta. Let's cancel those two. And then I'll have plus. So I have to divide this stuff by U. Let's do YR over U star minus 1 delta R. Okay. So this will be our like final simplified delta beta equation. And we'll put it in a matrix in a second. But so that's our first equation, but we had two equations here. We also have this one, this delta R dot equation. We want to write this in terms of beta as well. So this delta V term, we're going to change that. So in V, oh yeah, U star delta beta, so that's delta V, plus in R delta R. And we want to do the same thing that we did with YV, that we did with NV. We want this to be a partial with respect to beta now. And you can go through the same line of reasoning, but it's going to get you to this place. Basically, in beta is, you just need that factor of U star. So then we're going to have delta R dot is going to be, so these U stars are going to cancel here. So I'm going to have in beta delta beta plus in R delta R. Okay, and we're finally at the end of this simplification of the Dutch roll. We went from a fourth order to a second order, and we're just going to put these two equations that we just got into this matrix form. So the delta beta equation, it's 1 over U star Y beta, and then 1 over U star YR minus 1, and then in beta, and then in R. So they have this in the Nelson textbook. And now we have the details of where the heck they got this. Okay. So now that you have this simplified second order model, it's straightforward to get the characteristic equation. From the characteristic equation comes the roots, and the roots dictate your stability, your settling time, all of this stuff that you're going to want to control. So having this simplified model gives you the advantage of having an analytical expression for all of this stuff. And you can do the root locus analysis. We spent a day doing root locus with the longitudinal simplified equations. So you could do the same kind of root locus kind of stuff with this. So if you have a matrix equation, like a state space model, this is the characteristic equation. So determinant of lambda times the identity matrix minus this A matrix that we derived. So if you do that math, we're taking the determinant of this matrix. So just to remind you of a determinant of a 2 by 2, you're going to have top left multiplied with bottom right plus, well, it'll be that. And then I just multiplied this stuff out. All stuff that you guys have done before. You are experts. Like with this second order form, you know that this term is the natural frequency squared. You know that this coefficient of lambda is 2 times the damping ratio times the natural frequency. So you can get analytical expressions for the damping ratio, the natural frequency, the settling time, etc. Did that top right term in the matrix change signs? Yes. Okay, yes, because we're subtracting it here. Good question. So everything should be, yeah, because like this changed signs. This did. Yeah, good question. Just because we subtracted that bad boy. Okay, so basically what I'm saying is, okay, it's great. I get this analytical expression for the characteristic equation. I can say that how I can analyze how a specific term affects the dynamics using root locus. Da 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 da. Okay, but here's my beef. Here's my beef with this model. This approximate model for the Dutch roll leaves much to be desired. Well, at least if you're looking at the 747. And this is what I mean. Let's consider this flight condition. This is what we've been looking at. Flying straight 774 feet per second. I forget what altitude we were looking at, but whenever we've been playing around with the 747, I've been using the same flight condition. So we can just go back to a prior set of notes to get more of the details. But what I want to do, we have numbers for each of the elements in this matrix. So let's see here. So here's our simplified model, but I just plugged in the numbers for the 747. And if we grab the eigenvalues, there's two of them, and they're complex, which is good because this is an approximate model for the Dutch roll. The Dutch roll has complex conjugate roots, so at least we have that. Excuse me. What I want to do, get the natural frequency, damping ratio, settling time, compare that to the actual Dutch roll from the full model that wasn't simplified. And let me give you a couple cheat codes, as you guys mentioned before, some dynamic systems cheat codes. Here's the fastest way to get the natural frequency and damping ratio. So we have the complex plane right here, imaginary and real, and we have these two roots, complex conjugate. So let's take the positive conjugate of this root. So it has a negative real part, good, that means it's stable. And then we have the imaginary part. And this is not to scale, but so the real part, the magnitude is 0.0941. For the imaginary part, the magnitude is 0.8628. And here's the location of the root. X marks the spot. Okay. Cheat code number 1. The natural frequency is the distance of that root from the origin. So you can just use the good old Pythagorean theorem. So the distance of that root from the origin is the square root of the length of one side of the triangle squared plus the length of the other side squared. And this will give you the natural frequency in radians per second. So this is 0.8679 radians per second. Easy peasy. Okay, now moving on to the damping ratio. This is the second cheat code. If you look at the angle in here, from the negative real axis up to the line that connects that root to the origin, you could call that angle, I'm just making up a name for it, theta. The damping ratio is the cosine of that angle, theta. So how do you get that angle? Well, that should be the inverse tangent of this side, the imaginary part, divided by the real part. So that and there, that should be theta, right? So we take the cosine of that angle. If you do that, 0.1084. That's the damping ratio. I think that's the fastest way. Now, okay, no. The settling time, this is the 98% settling time I'm talking about. It's approximately 4 divided by the damping ratio times the natural frequency. So you just take the product of those two things we calculated up above. And this is predicting that once we start this Dutch roll falling leaf motion on a Boeing, it's going to take 42.52 seconds to resolve itself. Okay, that's what the approximate model says. If we go back to our full fourth order model, before we did any simplifications, I already got the eigenvalues associated with the Dutch roll, and they are these. They're complex. You can see already the real part different. The imaginary part, not super different. You're looking at 0.86 versus 0.95. But the real part is significantly different. Okay, let's just blast through this. If I use the same technique, this is what I got for the natural frequency, 0.946 radians per second. If we compare that, okay, 0.8679 to 0.946. I think that's pretty reasonable. What is that in hertz? Cycles per second. So 0.8679. Wait, how did I do that? This conversion always, I have to think carefully about it. I think I just divided by 2 pi, right? .1 cycles per second. And then the real one is 0.15 cycles per second. Okay, that's pretty close. That's actually reasonable. Damping ratio, what about that? I think this one's off. .0356 compared to 0.1084. So with the approximate model, we way over predicted the damping ratio. And you'll see this in the settling time. Because this has a smaller damping ratio, in real life it takes much longer to settle. 118.76 seconds, so 2 minutes. And this one takes 3/4 of a minute. So the settling time is significantly off. So if you design a control system for the Boeing with the intention of maybe damping out this Dutch roll if it ever gets excited, you're going to be basing that control system on a model that isn't a super accurate representation of the Boeing 747. But something that you should know is that, you might have heard this before, maybe not, but any models that we have for real life systems always have errors. Because they are abstractions of the real thing. Like even the model that I'm calculating this Dutch roll mode from is a linearization of the nonlinear dynamics, right? So even that was an abstraction of the real thing, making some assumptions about how small certain variables are. All that to say, when we design controllers in real life, we account for the fact that our models have some errors. And we design controllers that are robust to those errors. And the controllers tend to work. So yeah, my point is this simplified model, it has some errors, right? It over predicts the damping, and I think that's the biggest issue. But still, when we design a controller based on this model, it'll do a decent job. We'll see. We'll design controllers later on. We'll see. Okay, let's move on because we have two other models to make. The Dutch roll was the most difficult. Spiral mode is a little bit more straightforward, and the roll mode, you're just going to laugh to yourself. The simplifications that we make. Okay. The spiral mode, what the heck is it? If you just want to visualize the spiral mode in your head, it kind of behaves like a banked turn. So a combination of yaw and I say roll motion, but usually it's kind of like a fixed roll angle or maybe a very slowly changing roll angle. So it's like we have this maybe kind of circular path that the aircraft is navigating. And it has its wings kind of tilted in to the turn as it's going around. Now, this is like the style of turn that a commercial aircraft is going to do. And the reason that they bank during the turn is so that the side force is reduced, so that your drink doesn't spill into the aisle or onto your Nintendo Switch. So the first approximation that Nelson makes, considering that the side force is somewhat minimal because of the banked turn, the side force affects the lateral velocity equation. So the approximate model neglects the delta V dot equation. And I'm going to have the 4x4 matrix below here, and we're going to like cross out different stuff. Okay, so further, the roll angle is assumed constant during this banked turn. So like I said, the real spiral mode, the roll angle slowly changes over time. If you have a stable spiral mode, your wings will level out and the roll angle will go to 0. If you have an unstable spiral mode, the roll angle increases. You kind of go in this tornado motion towards the ground, and it's trouble, unless you correct for the motion. Okay, so we're assuming the roll angle is constant. Now, if the pitch angle is nominally also 0, meaning the nose of the aircraft is kind of level with a flat earth, this implies that any change in my roll rate is 0. So delta P is your roll rate. Well, this also implies that the derivative of my roll rate is 0. So like my roll acceleration. And just like we did for the Dutch roll, Nelson likes to assume that this inertia, let's just neglect it. Even though it is a very big inertia, it's just an order of magnitude smaller than the other inertia terms. So this is going to imply, like, whenever we see a star stability derivative, I don't know, I'm just making these up. they're going to revert to their unstarred form. Okay, here we go. We're going to take this fourth order model that we started with, and we're going to start eliminating things. So number one, this side force equation, we're just going to ignore it. We're going to throw it out. We're going to assume that, the nominal pitch angle theta star is 0, so the tangent of that's going to be 0. And that means that delta phi dot is equal to 1 times delta p. So this is saying that delta phi dot is equal to delta p. And we assumed that this is constant, so this is 0. If the roll angle isn't changing, then that's 0. But from here, this is equal to delta p, so delta p is 0. And what other assumptions do we have up here? Oh yeah, if this is 0 for all time, then delta p dot is 0. And these terms in this second column, these are the terms that when you do matrix multiplication, they're going to multiply with this 0. So like this whole column is going to be multiplying with 0. Okay. Okay, let's get rid of that. Good. Okay. All right, so let's keep working with this. From the second equation, so this delta p dot equation, well, number one, that's going to be equal to 0. And that's going to be equal to, oh, right, we said IXZ is 0. So like this is 0, this is 0, this is 0, this is 0. So those terms go away. And then all of these star terms just become the unstarred version. So this LR star, that's just LR. And that's just because we're assuming IXZ is 0. So now if I look at that second equation, I'm going to have LV, and this multiplies with this delta V. LV delta V plus LR, which is going to multiply with delta R. So that equals 0. So you could solve for delta V from this. And it's going to be minus LR over LV delta R. Okay. Next, I want to look at the third equation. So this third row right here. So delta R dot, that's going to be NV delta V plus NR delta R. And what I'm going to do is take this expression that we got, boom, throw it in right there. So this is going to be minus NV LR over LV delta R plus NR delta R. That's just substituting it in. And then we can just write this in a little bit nicer way. NR LV minus NV LR over LV, all of this times delta R. Oh, right. And then Nelson likes to, instead of using these V stability derivatives, to replace them with beta stability derivatives, just like we did with the Dutch roll. So we have these relationships. In V would be 1 over your speed times in beta, blah, 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 blah. So if we substitute, it turns out that we have NR L beta minus N beta LR over L beta times delta R. Now, this is just a first order model. The Dutch roll model was second order, so we had 2 roots, and they were complex conjugate roots. Well, now we just have 1 root. Whenever you have 1 root by itself, it's going to be a real root. You can only have complex roots if there's a pair of them. So this can be either a positive real number or a negative real number. Hopefully it's negative, meaning it's stable. So this right here, this is going to be the eigenvalue for this model. Or the root of the characteristic equation. And we'll call it lambda spiral. And just keep in mind, this is approximate. What I want to do, I didn't write it on the handout, but I want to compare this also to the 747. And I think I have that ready to go in MATLAB here. Let me see. Okay, so yes, all of this stuff up here, it's just parameters for the Boeing 747. And down here, this is our original 4th order model. Here was my Dutch roll approximate model that we derived beginning of class. That's how I got those eigenvalues. But here's our spiral. Let me just make sure this is the right formula. NR times L beta minus N beta times LR divided by L beta. Okay, let's run this. Let's run this code. So a spiral. Okay, that is the root for the spiral mode predicted by this approximate model. Now, if we take the eigenvalues of the original A matrix, these are the Dutch roll. This is what we compared to earlier. This one, so the other 2 roots are real roots. The slower one is always going to be the spiral mode. And you can tell which one is slower by the smaller number. The closer it is to the imaginary axis, the lower magnitude, the real part, the slower it settles. So we're comparing to this. So okay, let's write this down. Okay, for the 747, lambda spiral, this approximate is minus 0.0301. Lambda, I'll call this actual. The one that we got from the 4th order model is minus 0.0073. Now, when you have a real root, the main performance characteristic we look at is just the time constant or the settling time. What do you mean by the slower root? Let me tell you what I mean. Okay, so right here, I have 4 eigenvalues, 4 roots. And actually, you could talk about the speed of all of these roots. And when I'm talking about the speed of the root, I'm talking about the time constant or the settling time. The settling time or the time constant of a root is based on Wait, let's go back over here. Let's go down here. Okay. The settling time. So time it takes for system to decay takes system to decay 98% towards like a resting state. So wherever you position a linear system, if it's a stable linear system, if you just let it go and do its thing, it'll decay towards a resting state, which is 0 for linear systems. So the settling time is the time it takes for it to get 98% towards that final resting state. So for our purposes, it's basically like it has settled within that time. Okay, so the settling time this is the most general formula for it. I should put approximately. I think it's approximate. 4 over the real part of your root. Minus 4 over the real part of the root. So let's take the 747 for example. It has 4 roots. They each have their own real part. So the real part of lambda 1, which was like the Dutch roll, the first one, is minus 0.337. And that is equal to the real part of lambda 2 because they're complex conjugate. They're the same. So that Dutch roll, whatever. The real part of lambda 3, which is going to be the roll mode, is this, which we haven't gotten to that yet. We're looking at the real part of lambda 4, which is the spiral mode. And I said this is the slowest. Okay, so why do I say it's the slowest? Let's get the settling time for each of these. So for the Dutch roll, it's minus 4. Is it just the real part because the Euler identity keeps the real part in the exponent, but the imaginary part to the sine and cosine? You are exactly correct. The real part dictates the speed of the exponential decay. And the larger the magnitude of the real part, the faster the decay is. And then a byproduct of the exponential decay is the settling time. So minus 4 over minus 0.0337. 0.33. So yeah, oh yeah, we already calculated this one. Like that, so that's how I calculated that this one was like 2 minutes for the Dutch roll. This one, 4 divided by 0.5606, 7.13 seconds for this roll mode. And this one's going to take a long time. 4 divided by 0.0073 is 548 seconds. So if you want to look at a system, and so the overall settling time of the Boeing is the slowest of the slows. Because generally, as you're flying through the sky, you might excite any number of these modes, and so you're always going to be waiting on the spiral mode, I guess. Unless you stabilize it with a controller or the pilot themselves kind of corrects for it. But I hope that gives you an explanation or a good idea of how you can determine which is the slowest route. It's going to be the route with the lowest, the smallest real part. Smallest in magnitude, that is. Okay. Wait, okay, so let's get the settling time from down here. This helps us. So the actual settling time is like 540 seconds of settling. So out of the 4 roots, 2 will have the same real part, which is the Dutch roll. And you can tell the other 2 apart by the settling time. You're exactly right. If you're given 4 roots and they tell you, okay, this comes from a lateral flight dynamics model, you would be able to say, okay, right here I'm looking at the Dutch roll. Those are the complex roots. And then from the other 2, you're like, okay, which one's slower? Okay, the slowest, that's the spiral one. You're an expert. People will be like, how did you know that? And then you won't tell them. You'll keep it a secret because you should never reveal your tricks as a magician. Okay, so obviously now you know that this is going to predict a much faster settling time because between these 2 roots, I know that this is the slowest one. So, okay, let's calculate it. 4 divided by 0.0301. This predicts like 132 seconds. So, at least for the 747, that's significantly off, right? That's a huge error. Maybe for a different aircraft, it wouldn't be so bad. But this is what Nelson prescribes. Excuse me. Okay, we have one more mode to get an approximation for, and that's the roll mode. Now, the Nelson roll mode approximation ignores everything but the roll rate equation, delta P. And within the roll rate equation, they only retain the terms delta P. So it becomes a very simple equation. Okay. Delta P dot, the time derivative of my roll rate, is LP delta P. Why did they ignore delta phi? That's a good equation. That's a good question. So we have, let's go up here. And I know this one's kind of cluttered, but that's a really good question. Let's look at this delta phi equation. I mean, I'm assuming, yeah, we're going to assume that this nominal pitch angle is 0. So the delta phi equation is going to be this. Delta phi dot is going to be equal to delta P. So if we kept that, we would have this like second order system, right? And what would it look like? It would be LP 0, 1, 0. Wait. If you do that, that gives you a 0 eigenvalue, right? Oh, that makes sense. And the coefficient for delta phi in the delta P dot equation is 0. Yeah, right. They're also ignoring, well, delta P, it multiplies that delta phi term with the 0 anyways. Oh, you know what? I think I have a good idea for that. Because let's talk about what the roll mode is physically doing. they're looking at it as a pure rolling motion. So if I have an aircraft and it's just looking right at me, and then I roll with some rate p, the over time, let's say that the rate, well, hold on a second. First of all, this is a first order system, and if it's stable, let's plot the roll rate over time. Like if maybe I start with some non-zero roll rate. Because this is stable, it's going to slowly stop rolling over time. And we found that the settling time was like 7 seconds or so. So it'll roll for like 7 seconds, and it'll get successively slower, and then it'll stop rolling. So, but if I imagine how that's happening, so I have some initial roll rate, and then this like moves around, and maybe after 7 seconds, it's like, well, who knows? Maybe it's upside down. Maybe it looks like this now. And we're flying upside down, and it stabilized me with this like 180 degree bank angle. So that means if I plot our bank angle over time, it's increasing, and then it like goes to some non-zero value. Now, whenever you combine a system like this in dynamics, where one of the states doesn't go back to zero, but it like stabilizes at some non-zero point, you'll get a zero eigenvalue. So whenever you see a zero eigenvalue, that's what it means. It means something didn't come back to the origin. And we can prove it with this. So let's like take this A matrix. And we're going to name it after you, because this is your approximation. How mia, senor? And this is your fault. 0, 1, 0. Okay. Let's get these eigenvalues. Okay, so you got the 0, and then you have the minus 0.4336. So if you take the Nelson approximation, though, which is just LP, then you just get this. So I think the reason they throw out that theta is it's just kind of if you wanted to recover that delta, or wait, sorry, I'm saying theta. If you want to recover that roll angle after the fact, you can do it. You can integrate the roll rate and find out what that angle would have been. But I don't think having that 0 eigenvalue is going to add like too much value to the model. Okay, let's compare the settling time. So in this case, this is our root, lambda roll. And the settling time based on this approximate root, let's go over here. It's just going to be minus 4 over lambda roll, which is just, why don't we just call it LP? Minus 4 over LP, the stability derivative of the roll rate with respect Wait, the roll moment with respect to the roll rate. Okay. TS roll approximate is -4 divided by LP. 9.2 seconds. And then the actual settling time is 4 divided by that number, which is 7 seconds. So this is actually the best of our approximations, which is kind of funny too, right? That this particular model, it's the simplest of all of them. It seems like we did the least amount of work in coming up with the model. And it's like, oh, that's our best one. So that was 9.23 seconds compared to 7.14 seconds. Not bad. Okay. So guys, that is what I wanted to do today. I wanted to say there's 3 lateral flight modes. There's Dutch roll, there's spiral, and just vanilla roll, just the regular roll. And we have 3 models, and some of them are better than others. And the reason that we have these models is reduced order models are better for control system design. It makes it a little simpler. But it comes at the cost of the models lose some fidelity, as we showed here. At least for the 747, there are significant errors that are incurred by using this Nelson approximation. Like I said, these are not the only approximate models, but they still are pretty popular, and I think we'll be working with these for making some controllers for the rest of the course. So that's why I'm showing them to you. I'm going to turn back on a little bit of these tunes. Today's Wednesday. Okay, I don't have office hours today for flight, but I have office hours tomorrow. Saeed, our TA, has office hours tonight, though, starting at 4:30 on Discord. So Nick says, I was going to hit the TA's office hours. In the meantime, I emailed you and was hoping you had time to get to it. If you have time, can you check your email from... Okay, cool. Yeah, let's pull up this question here. Oh, okay. Gotcha. Let's look. So, okay. While performing the first question on the homework, I got through the first 3 parts. When part 4 comes up, I'm confident we have to build the whole state model. Okay. In which I have the A and B matrices, but finding the state and input vector is confusing me because they're composed of perturbation variables. I see that we are told that W star and theta star, so those nominal values, are 0 in part 3, but I feel as though I'm missing something else in order to calculate these. I know the general equation would be delta U is U minus U star, right, but I'm not sure what I would use for U. Okay, let's take a peek. So part 4. Wait, are you talking about... Hold on, I'll check this real quick. First 3 parts. Are you talking about part D on that question? part D. How Amia Senor says, we're given the Mach number and speed of sound to find U star. That's true. Let's go back here. Now, oh yeah, build A and B, that's right. So if I pull up where's our longitudinal? Good gravy, I need to find this thing. I got the one for you, but like calculating delta W, confused on the general process. Okay. Longitudinal. Wait, so are you talking about if you're just getting the A and B matrices, these parts themselves are not based on the perturbation variables. Calculating delta W. Calculating delta W. Oh, the X vector attached to A, I see. Okay, for none of these parts do you have to actually calculate that vector. So this vector is always just delta U, delta W, delta Q, delta theta. These are just the names of those variables. So if you're thinking that you need to like assign a number here, just the same way you would assign a number in your A matrix, that's not what you do. Is that what you're asking about? I don't know if I'm understanding exactly, but like the first four parts of the homework, those just have you build the A matrix, the B matrix, calculate the eigenvalues and stuff. And none of that is actually involving calculating delta U, delta W, delta Q, delta theta. Those things you calculate by integrating these equations over time. Does that answer your question? Because I can expand more if that's what you need. Okay. Okay, cool. Anybody else have homework questions? Whew. Hey guys, we are halfway through the week. Wednesday. Then we have next week. But the week after that is Thanksgiving. And it is a time to get some recuperation, hopefully. That is my hope for you. On question 2, how is the angle of attack related since it is not explicitly in the equations? In question 2, how is the angle of attack related since it is not explicitly in the equations? The aerodynamic force and moment generated on the airframe for an angle of attack aerodynamic force. Okay, what this question is talking about, it's not, I mean, it is connected to this model, right? But this is asking about a subset of the model. It's just asking about the moment or the force. So where is that? Like if you go to Nelson chapter 3, these two equations, these are expressions for the aerodynamic forces, that's X, Y, and Z. Aerodynamic moments, L, M, and N. So that question 2 is talking about if I introduce a perturbation in whatever it's asking about, how is that going to then affect these moments? Now, it's related to the flight condition that we give because these stability derivatives are different depending on how fast you're going, your altitude, etc. So that's why the reference flight condition is important. How would you separate damping ratio and natural frequency when they're always attached? What do you mean? What do you mean, brownies? How do you separate them? I mean, we separated them here. Well, okay, like eigenvalues give you the damped frequency. Oh, yeah. I see what you mean. Like when you get a pair of complex eigenvalues, the standard second order form is you have the damping ratio times the natural frequency plus or minus the damped natural frequency times I. But the damped natural frequency is also a function of the natural frequency and damping ratio by here. So there's a bunch of ways to separate these two things from this point. Excuse me. Because for example, let's say you have like these are your roots, right? Just as an example. This would give you two equations and you have two unknowns. So like the first equation would be these real parts are equal to each other. Okay, so I have that. And then you have a second equation, which is omega n square root of 1 minus zeta squared would equal 3. And so you can solve these equations together, like do a substitution. And that's one way to do it. But there's other ways, like these roots. This is the way I like to do it. If you draw them in the complex plane, you have like imaginary, you have real. Say my root is here. The imaginary part, or that the real part is, well, the magnitude of this is zeta omega n. That's the real part. And then the imaginary part is omega n square root of 1 minus zeta squared. And if you do the trig analysis on this, well, you would find that omega n is the distance from the origin to the root. And you'd find that the damping ratio is the cosine of this angle in here. And that's the way I did it earlier in the lecture. Like if you just have two numbers for the roots, using this geometrical interpretation, it's really easy to just quickly calculate those things. But if you're looking for like more of a system of equations way of doing it, you can do it this way. And I think there's 2 or 3 other ways that I'm not even remembering right now. Oh, another way, like from the characteristic equation, the standard second order form of a characteristic equation is this. So if you have your characteristic equation, like it's lambda squared plus, I'm just going to make up some numbers. This gives you a different system of equations. I have omega n squared is equal to 10, and 2 zeta omega n is equal to 5. Actually, this is easier, because then you'd have omega n is the square root of 10. And then I'd have zeta is 5 divided by 2 omega n, which is 5 over 2 square root of 10. That one's also easy peasy. Three different ways. Okay, everybody, I need to run to office hours for road vehicle dynamics, but I'll have office hours for this class tomorrow at 4:30. So if you have other questions, you can come see me, but our TA is offering office hours tonight, so you can go talk to Saeed. Hey, you're very welcome. Thanks, you guys. Thank you for your attention, your participation. It is a privilege to hang out with you Monday, Wednesday, Friday. It really is.